In section 3.7 we're looking at recurrence relations, and here we're going to exploit our new notation, our UN notation. So we can have things like U1 or U6, which means the first term of the sequence or the sixth term of the sequence. But we can also say things like this, and I'll well, no reason not to, I will stick with what the book says. So I can relate the terms of the sequence to each other. So this says the second term of the sequence is 2 lots of the first term of the sequence, add 3. Okay? So if I know what the first term of the sequence is, if I say U1 equals 4, then the second term of the sequence, I'll stick with the book. The book has U1 equals 6, so U2 equals 2 times 6 plus 3, so U2 would be 15. Okay? Now that's fair enough, but that only tells us about the first 2 terms of the sequence. But what if we do something like this? We say UN plus 1 equals UN plus 4. Let's think about what this means. This means term number n in the sequence. This means term number n plus 1. So when n is 1, this is the first term, this is the second term. But when n is 2, this is the second term, this is the third term. So this tells us how consecutive terms in the sequence are related to each other. Okay? So if I now tell you U1 equals 6, and this is true, then I'm telling you that U2 equals U1 plus 4. Okay, so this is true for any value of n. So we'll start with n equals 1, and I get this. So that tells me that U2 equals 10, right? That was when n equals 1. What about when n equals 2? When n equals 2, U2 plus 4 equals U3. So U3 equals 10, because 10 is U2, plus 4 is 14. U4 equals U3 plus 4, so U4 equals 18, okay? So this is what we call a recurrence relation. So recurrence, like reoccur, sort of happen again. So you get from one term to the next, to the next, to the next. And this is a bit more of a sophisticated way of thinking of a term-to-term rule. So if we had a sequence 6, 10, 14, and so on, we'd look at that, 14, 18, and so on. We'd say, well, the rule here is add 4 every time. Well, this is just a neat mathematical way of saying that with some algebraic notation that we then might be able to use to do some fiddly things. We usually use a U, but if you look in example 20, we can do that with an A as well. So they've given us a recurrence relation that looks like this. A1 is P, A2 is given by, A1 is P, AN plus 1 is given by AN squared take away 1. So in other words, A2 is A1 squared, which is P squared, take away 1. A3 is what we get when, so we've done n equals 1, and we've got A2. Let's do n equals 2. We get A2 squared minus 1. Well, A2 is P squared minus 1 squared minus 1. A2 squared minus 1 equals n plus an plus 1, so A3. Okay, so A3 equals this expression here. And if we simplify that expression there, we get what they're asking us for in the thing, p to the 4 minus 2p. So I can get a sequence here which goes p squared minus 1, and then p to the power of 4 minus 2p. So it's a complicated series, complicated expression, complicated sequence is what I'm trying to say. But, that's fine. We can have a sequence with p's in it. That's not a problem. So, we can, that's how recurrence relations work. They relate the term in the sequence to the next term in the sequence. It's no good just to have a recurrence relation that says an plus 1 equals an minus 6, for example, because this tells us, well, to get from one term in the sequence, you take away 6, that tells you the next term. But what's the sequence? I don't know, because I don't know where to start. Now, if I come along and tell you, well, an equals 7, now I can write the sequence down. It's 7. To get from this term to the next term, you take away 6. Then to get from this term to the next term, you take away 6, and so on. So now I can write my sequence down. what else can we do with these? I think this is more or less... Oh, yes, so a couple more things. There's nothing wrong with doing it this way as well. This tells us the term you're on and how to get to the next term. We could think of it like this as well. Take the term you want, take the last term, take the term before the term that you're on, and take away 6 from it. So if you want the second term in the sequence, take the first term and take away 6. If you're on the second term in the sequence, take away 6 and that'll give you the third term. So these two recurrence relations really say the same thing. Okay? Now, the other thing that we can have is, well, let's take example 20 because this happens to deal with, well, no, let's not actually, let's move on. So we can have increasing, decreasing, or periodic sequences. So an increasing sequence does perhaps what you think, the terms get bigger. Well, how do we write that? Well, if the terms are constantly getting bigger, then the next term is bigger than the term we're on. So un plus 1 is bigger than un, okay? If it's a decreasing sequence, the next term has to be smaller than the term that we're on. Okay, so increasing and decreasing sort of do what you think they do. Now a periodic sequence is something that might look like this. I don't know, 2, 5, 7, 2, 5, 7, 2, 5, 7. So I just get 3 numbers that go round and round and round, 2, 5, 7, 2, 5, 7, 2, 5, 7. That would be a periodic sequence. So how do we write that? Well, in this case, un plus 3 is the same as un. Okay, so if I take this point here, and I call that un plus 3 is 1, 2, 3 numbers along, which is that one there. And any point in the sequence, if you go 3 steps further on, you've got the same number that you were on. So un plus 3 equals un. The way that they've written that in the book is, if it's a periodic sequence, un plus k is equal to un for all possible values of n. So they write that as for all n which are natural numbers. And there is some k where that is true if you've got a periodic sequence. So, and k is then how long is the loop. So if this is a loop of 3, then k is 3. If it's a loop of 17 numbers and then it starts again, then k is 17. That can be called the period, it can be called the order of the sequence, okay? Now, last couple of things to say. If you've got a sequence defined with summation notation or with recurrence relation notation, it's not always obvious. Sometimes it's obvious. You can see that it's an arithmetic progression or a geoarithmetic progression, or you can see what kind of thing it is. If it's not obvious, write the sequence out. As I'm very fond of telling my class now, if in doubt, write it out, okay? So if you're not sure what the sequence looks like, write the sequence down. Write down the first few terms, and then you should be able to spot what kind of sequence it is. If it's arithmetic or geometric, we can use those techniques from earlier in the chapter. If it's a periodic sequence, then we can do sort of useful things with it. So let's take this sequence that I've just made up, 2, 5, 7, 2, 5, 7, 2, 5, 7. If I want to do the sum of the first 10 terms of this sequence, well, 2 plus 5 plus 7 is 14, right? And if I'm going to do the first 10 terms, then I'm going to get 2 plus 5 plus 7 3 times. So I get 14 3 times, and then I get, and that's the first 9 terms, and then I get the 10th term as well. So I'm going to have to add on a 2, right? If I want to add together the first 50 terms, what would that look like? Well, I'm going to get 2 plus 5 plus 7. How many times am I going to get that? Well, I know that 3 fits into 48, right? So 14 is 2 plus 5 plus 7. If I do 14 lots of 14, I've got the first 48 terms, all right? It's a slightly unfortunate example. Let's change this to, I don't know, 53, just so that we don't end up with 14 twice. So I know that 3 fits into 51, right? So if I do 17 lots of 3, then that's 53. So I do 17 lots of the first three terms. Well, the first three terms add up to 14. So I do 17 lots of 14. And then that is the first 51 terms dealt with. So I need terms 52 and 53. So that's going to be a 2 and a 5, because it's going to be the first two terms of the next cycle of 3. Okay? So I can add together the first 53 terms of this sequence by doing 17 times 14, add 2, add 5. All right? So these periodic sequences, if you write the sequence down, the questions they can ask you might not be simple, but they follow that sort of a pattern. If you got the sequence written down and you think about it and use a bit of sense and use the other facts we know about sequences and algebra and things, we can get there from there. Now the last thing to say is section 3.8, modelling with series and sequences, is essentially these are some questions in context. I don't think there's much for me to go through here. You're going to have, I mean, there are a couple of examples, but you can read them perfectly well out of the book, and even then there are just examples. There are no new mathematical techniques. As you're used to by now, a lot of these chapters have a modelling section at the end. That's because the exam board are very keen on putting emphasis on questions in context, and so they put in an exercise with a few examples just to get you practicing questions in context specifically. We should just take that as a hint that there are going to be lots of questions like that on the exam, so practice them carefully. Whatever it is, there is going to be, there's no particular need for me to go through example 22. Even if you're stuck in example 22, it's not that example that's going to come up, right? There's no new techniques for me to show you here. Just read the question, realise that they're describing some sort of sequence of numbers. If in doubt, write it out. So write the sequence down if you can, and then once you've got the sequence written down, hopefully you can apply some of your sequences knowledge and get an answer. So that is the end of chapter 3. There we go.